Welcome. My name's James Wormold. I'm a writer here at Europa Science, publisher of Imaging and Machine Vision Europe. So in today's Visionaries web panel, we'll be discussing the latest developments in optics and imaging, and how selecting the correct lens, specifically for individual applications, can be critical to achieving optimal performance. Helping us study the subject in closer detail will be three industry leaders who will be sharing their insights and experiences on the topic. So please welcome Tom Armsback-Young, who's a Vision Solutions Engineer at Edmund Optics, Simon Hickman, who's Managing Director of Multipix and also Chair of the UK Industrial Vision Association, UKIVA. And apologies to anyone tuning in expecting to see DeGould CEO Matthew Holloway. Matthew's had a last-minute diary change, so won't be able to join us, but we'll be hearing from DeGould's head of R&D, Spiros Karachalios, instead. Welcome, gentlemen. I should point out at this stage, by the way, that the web panel discussion will be available on demand alongside others in the Visionary series on the Imaging and Machine Vision Europe website for 12 months after today, in case you'd like to recap any of the information you hear. But moving back to the present day, I'll run through the web panel schedule quickly. We'll start off with some short presentations from our speakers, explaining who they and their companies are and their role within the optical solutions sector. Then we'll move on to the panel discussion, where I'll throw up some questions for them to answer. If you're watching live, there'll also be an opportunity to type in your own questions you'd like answered as well. I see we've already got some questions come in, so that's great. So our three speakers are all chomping at the bit to introduce themselves by now, so let's see them crack on. So Spiros, if you could start us off telling us a little bit about yourself and your work at DeGould.
Sure. Let me just quickly also share my screen. All right, you should be able to see my screen now, right? Great. Well, thank you very much for having me. It was a bit of a short notice. Unfortunately, Matthew, as we said, he will not be able to make it. I'm Spiros. I'm the head of the R&D at DeGould, and I'm just going to give you a bit background information about what DeGould and what we do. We are basically enabling the OEMs to reduce their costs by increasing their quality inspection and assurance. We are assisting them in handling their claims and providing, trends and insights on terms of where the defects are occurring and how they can reduce them basically and make their vehicles more quality. We are currently in quite a bit of locations around the world. We are, I think, here it says we have around 2 million vehicles per year, but I think at this point this is a bit outdated, and we are way exceeded that. And we offer a bit of a variety in terms of quality for the inspections, in terms of either defect detection, that would be like chips, scratch, dents, dings, and then we offer like spec check information about things and parts that have been fitted or fitted incorrectly or they are missing and so on. And we are in various places in the whole inspection process. And this is like a big overview of what the inspection process looks like, where we can start like from the body shop area, right from the beginning. Then we go into like paint and assembly. We go into the finishing line. We have systems that are in the vehicle logistics, in the outside, and right up until the end where it goes into the dealerships and, users can actually claim, defects directly from the manufacturer and the dealer. So it's the whole process basically. And our solutions is what we call the auto compact system. This is the main system that is going into production line, conveyor-based production line. And the main selling point and proving point is that it is capable of detecting more defects and more accurately than the current inspectors, which means we are giving them the ability to move from the inspection line and go down into servicing and repairing basically. There's also, we have the auto scanner, as I said, for the outside environment. It's fully weatherproof. Again, we can get high resolution images of the vehicles. For the body shop is what we have the auto compact, the stereo vision module, where we can detect defects and we can measure gap estimations between the panels. And then in the dealer side, we have what we call the DVM app, which is the app, either iOS or Android, that gives the ability to the users to go in and claim back defects that they find in their vehicles. On the dashboard, again, I'm rushing through this as I'm just going to give you a bigger context basically on what we do. This is a dashboard, what it looks like, and we can, again, the users can go in and see their the problems with their vehicles. We can give trends to the to our customers of where usually the defects are. Now, in terms of designing the system, the main thing that we do is we create digital twins. We have realistic simulations of what the actual environment will look like, and we are tailoring the system for them. And here you see some examples of, reality versus simulation versus augmented reality. These are things that our customers want to see, and it is a very good proving point that we can simulate something at the beginning, and then you can prove that it actually is realistic, and you can give them more confidence that the system can work. There are things that we are considering in terms of the lenses and the sensors, like field of views or overlaps, or we are evaluating the resolution or the focus quality. All of that can be done beforehand in simulation mode. We're talking about depth of fields and exposure values, and then we move into the lab testing, and we basically install the system and make sure that it produces the same results as we have found in simulations. So we are talking about measurements like MTF or chromatic aberrations. We are trying to make sure that we select the best lens and the best sensor for that specific application. That was a very quick run through. Again, if you want to learn more about that, just pop in an email or give me a call, and I'll be happy more to discuss with you more.
Excellent. Thank you for that, Spiros. That's all really impressive, but also anything to help auto manufacturers reduce their costs, I'm sure, is great to hear for them. Now, Thomas, if you're ready to tell us about your role and the work of Edmund Optics.
Yep, sure. So first of all, thanks for having me. It's a pleasure to be here today. So my name is Tom Alpsbach-Young, and I'm a vision solutions engineer at Edmund Optics. And so basically my role consists in providing technical feedback and analysis for standard, but also custom projects that come in from our customers in Europe. So just a little bit of background on Edmund Optics. So we're a global optical solutions provider, so components, but also solutions, since 1942. We're a family-run company, and now we're in our third generation of Edmund leadership with Mary Edmund. We've got just over 1,200 employees globally. I think the main point here as well is the number of manufacturing facilities that we have. We have 8 manufacturing facilities across the world. I'll go into a little bit more detail on the next slide for that. But we also have 6 global warehouses to allow for fast shipment as well of our optical products. So as you can see here, this is what our global footprint looks like. Most of our manufacturing is either going to be in the US or in Asia. And specifically for imaging lenses, our main 3 sites will be Malaysia, China, and the USA in Arizona. Yeah. Our company is a little bit different, I would say, to most OEM providers. We've got a split in our company, basically, where one division, let's say, of the Edmund Optics is called Marketplace. And this, you can kind of think of it as a one-stop shop for every optical product that's imaginable. And so with this, the goal is to have as many different types of products from different vendors. So not only the optical products that we manufacture ourselves, but also from different third parties across the machine vision industry, but also across the other photonics branches that are out there. But the other division that we have is called manufacturing services. And this is very much focused on our own capabilities. So all the products that we manufacture ourselves, and that can range from anywhere from your standard components like singlet lenses, from polarizers, beam splitters, all the way to more complex assemblies like imaging lenses or advanced assemblies. And as you can see, this manufacturing services division is split into a further 4 categories based on the type of products that we offer. So each of these categories will have different manufacturing sites that are dedicated and specialized in their respective fields. So from precision optics, which is, again, your standard beam splitters, your singlet lenses, aspheres, mirrors, prisms, to filters, and then you have also the laser optics division, which is basically very similar to precision optics, but more tailored towards high-powered laser applications. So specialist coatings and things like that would apply here. And then finally, the one that I'm going to focus the most on is imaging optics division. And this is basically the type of product that we would offer here. So this is not only our standard product, but our custom products we would offer with this. So custom assemblies from M12 lenses, fixed focal length lenses, telecentric lenses, zoom or varifocal lenses, and then microscope objectives, or even fixed magnification lenses as well. And yeah, I'll pass it back over to you.
Thanks, Tom. Edmund's a huge supplier and manufacturer, of course, but it's great to hear about some of the individual help that you're providing for bespoke systems and solutions as well. Simon, next, did you want to introduce yourself and your role with Ukiva and your work with optics a little?
Yes, hello everybody. My name's Simon Hickman. I am the managing director here at Multipix. We are a distributor of machine vision components, but really we do a lot more in the way of recommendation of the right products and so on in all those categories. One of those categories being optics. Actually, quite a specialist subject for me over many, many years. And so therefore have quite a deep knowledge on selecting mainly standard optics rather than custom optics. Been involved in a little bit of custom optics in the past, so can sort of share a little bit of that along the way. But yeah, so Multipix has been in this business for over 25 years. So we have a huge experience in many different types of applications. But when it comes to optics, I mean, there are some fundamental building blocks, which I thought Spiros actually mentioned a few, and Tom. But it all comes down to sort of 4 or 5 different things that come into any choice. And we'll probably touch on those subjects time and time again. One being MTF that Spiros mentioned, MTF, modulation transfer function, which essentially is to do with the resolving power of the lens. So-called line pairs being a black and a white line, and how easily you can distinguish the white from the black lines. As those black and white lines get thinner and thinner and closer together, you end up with optical blur that makes those lines not white anymore, but a light grey, and not black anymore, but a dark grey. And as you approach the optical limit of the lens, the kind of tones of those lines all become one, and it's just one big blur. So fundamentally, that is kind of the biggest building block, I guess, MTF. And when you're talking about putting a lens onto a camera, you are thinking about what size the pixels are inside the camera, and that will then lead you to what might be the most appropriate lens from a resolution point of view. But it goes on and on through, the distortion, which is also, the wider angle the lens you choose, the more distortion it generally has. I've got to say, though, with distortion, It's probably one of the only things that you can compensate for post acquisition easier, let's say, than anything else. You can't get NTF back from anywhere. You either got the resolution there for nice crisp edges or you haven't. You can try and sharpen them, but it introduces all sorts of artifacts generally. Whereas with distortion, you can actually unwarp things because it's a constant always. So there's that. And then there's other things that were mentioned by the other two chaps, things like chromatic aberration, where we have different colors actually get focused at slightly different positions behind any lens. And therefore, when you're thinking about putting a lens onto a camera, if you've got lots of different colors involved, you have to be very careful about this chromatic aberration through lenses. Some lenses are much better than others. And there are things, are corrected for different parts of the spectrum. Lots and lots of theory behind, but the crux of it is getting into some nitty gritty, thinking about some applications. And that's where I've kind of been for the last 25 plus years. So hopefully that gives you a little flavor of, some of the stuff that I've been sort of touched on. But again, I'm sure that our details will be shared with everybody at the end. If there's any specific questions, I'll be very happy to talk about it. So that's it from my side.
Absolutely, yeah. Contact details will be on the website at the end. And if you have any questions that we didn't have time to get through that you'd like to send to our speakers, then do send them through. But without further ado, I'll get started with the Q&A part of the discussion for today. So the first question I had, which I think maybe go to Spiros to kick us off, is what are some of the key challenges that you come face to face with, either when you're designing, building, or optimizing lens-based applications, and maybe tell me about some of the techniques that you've developed to overcome them?
Yeah, so one of the major thing for the OEMs is to try and find the smallest defects possible that they can. They have, very strict requirements in detecting, scratches and chips that are even in the undercoat or the clear coat, we are talking about, sub-millimeter things, and we're trying to detect them from, a meter away. Using a camera, basically. So, in order to be able to overcome this problem and use lenses and cameras, you have to take into account things like, as we've been discussing, like motion blur, distortions, depth of field, and you have to design a system that can, produce and fulfill the requirements for the customer by taking into account all these errors that you have accumulating over and over again for you. Other things are like environmental factors, different light conditions, or different types of vehicles. We're talking about SUVs, vans versus very, very small cars. So how could you have a system with a single camera that can be finding sub-millimeter pixels, sub-millimeter defects on different types of vehicles from the same distance? So trying to design a system like this, you have to do a lot of simulation at the beginning. You have to really fine-tune all the parameters for the cameras and then start doing a lot of testing to accommodate all these problems, basically.
And Thomas, I mean, there's a lot of Tom, there's a lot of questions, a lot of challenges there that Spiros brought up. Are there any other problems that you can think of which you face?
Yeah, I think just to reiterate, I think environmental aspects is a key factor here. The testing required for that as well. Often you can't get away with just a standard lens to meet those environmental aspects, and then it means that you have to look into doing custom or at least semi-custom lenses. So things like temperature ranges, making sure that you can get that MTF performance across the whole temperature range at which the lens will be operating at without any performance degradation. So having that homogenization across the whole temperature range is something that's usually quite key. Other aspects as well, in terms of environmental as well, is things like ruggedization. Are we dealing with an environment where there's a lot of vibration or a lot of shock? is that going to affect the lens itself? Is there going to be displacement of the optical elements inside relative to the mounts that they're being mounted in? So that's some of the things that we have to take particular care at assessing when dealing with customer applications. Another aspect I would say is probably size constraints is something that comes up quite a lot. Often the lens is probably not the main part of the system that's being thought out first, and there's all sorts of other components to a machine vision system or to a robotics application or whichever application that we're dealing with here. And vision is often not, let's say, not the primordial aspect that's being thought out in these types of systems. And so we end up with having a lot less space than we would like as a lens manufacturer. Typically, we want as much space as possible. So having to design within space constraints it makes it really tough and ends up having much more complex lens elements inside, or which drives cost basically. So that's and manufacturability.
Right, and Simon, from your point of view with multi-pix, do your experiences line up with Spiros and Tom, or are there any other challenges or alternative ways of dealing with the same problems maybe?
Yeah, I mean, I agree with everything everybody said so far. Some of the other sort of, to go back over a few, like the environmental side of it, the vibration side, there's usually kind of set things that you immediately go to on that subject. Things like, you can imagine if you have any lens that has some kind of aperture control tends to have leaves that are they're kind of slightly interference fit generally, and as you close the aperture down, there are moving parts in there that, of course, if you vibrated a lot, could get damaged or fall off or whatever. So quite often something as simple as just replacing that iris control with a fixed plate with a center hole absolute is the answer. I mean, there are certain things you need to be careful of with that, and certain manufacturers actually provide that. So you have a feathered edge on the end of the actual orifice. It's also completely circular, which is quite nice, because you can imagine normally it's not quite circular because of those leaves that you're going in and out with. So there's some quite sort of, so easy, but it's not easy because standard lenses are inherently standard, which means you can't just go changing something very easily. Most manufacturers don't allow you to do that. So you've either got to take it on your own, or you could go for a custom setup, such as something that Tom might specify. Some manufacturers allow you to unscrew parts of the lens and put in these orifice plates or whatever. But, sort of going one step back, I would say one of the first things that you kind of establish when in any application is what Spiros was saying, and what that is the field of view and what working distance you have. And from those two parameters, you would work out what the focal length or the right focal length lens would be to achieve what you want to cover from the working distance. And there's a few other things that come in generally, things like if you're looking at a very small object, which a lot of the time is the case, then you tend to, one of the first considerations is how big is the object compared to the sensor of the camera, and therefore you work out what kind of magnification is required. Now, if it's a magnification of, let's say, 1:1, i.e. is a very small object that's pretty similar to the size of the sensor, then you would, rather than a sort of standard lens setup, you'd start to consider other types of lenses, such as telecentric lenses and macro lenses that I think Tom just sort of touched on. And the reason for that is that the design of the lens is a bit different. Everything's sort of turned around on itself, so that what would normally be behind the lens ends up in front of the lens, and vice versa. And the reason for that is that therefore you optimize things. And when I mentioned telecentric, telecentrics is a way of collimating the light. And I'm sure that most people that are listening to this would understand that at the focal certain focal distances, you have parallel rays, and that's what you want to achieve. If you've got nice collimated light, then you don't get magnification changes with distance. So they're fantastic for measurement applications, where you might get slight differences in distance. And as you do that, of course, if you've got a divergent lens, those defects appear different sizes. But with a telecentric setup, you don't get that. Also, if you're trying to recognize something in a field of view, if it's in the center, you might just get a nice planar top surface of what you're looking at. If it appears at the edges of the field of view, then you sometimes see the sides of that object, and wherever they are, you see a slightly different sort of down the side of the object. With a telecentric lens, because it's collimated, you see the object exactly the same wherever it appears in the field of view. So if you're trying to do some kind of pattern recognition or object recognition, that is a really key and a nice way to do it. So no perspective distortion, no magnification changes with distance. So you can see it sort of all stacks up to what we'd consider to be almost like a measurement class lens. But they typically, well, because it's collimated, the lens is physically the same size as the field of view. So I think, as Tom sort of said, you can't go, if you want to look at something that's a meter wide, in its telecentric lens you're after, you need a lens that's a meter diameter or bigger. And it's just not practical to do that in a lot of situations. So there's a lot of compromises along the way. And then really goes back on the rest of what we've said. There's some calculation packages, many around, that will allow you to do basic calculations, things for fields of view, where you have, if you Google it, you'll be able to find a very simple calculation for calculating working distance versus your field of view and all the rest of it. There's also online things for working out other things like so-called MTF. Now, we've mentioned it twice or three times now. This MTF, where things blur, it's measured in what's called line pairs per millimeter. So and it's not really used anywhere else, I don't think. It's really just sort of MTF is line pairs per millimeter is a unit that is quite unique. And to work that out, it's very simple actually. Line pairs per millimeter is just 500, the number 500, over the size of the pixel or whatever you want to measure, gives you line pairs per millimeter. So simply 500 over 5, let's say 5 microns that you wanted to measure to, or 5 micron pixels, equals 100 line pairs per millimeter. So it's quite an easy calculation. Again, all available freely online if anybody has a look. So when you start to look at these MTF charts, if you see line pairs per millimeter, it's nothing too difficult. It's just about getting your head around what those numbers mean. So all those things, I've probably exploded everybody's head already. So it's not real application stuff. It's just those considerations, as we said.
There's a lot of really complex difficulties to get through, but the technology and the techniques are there to help us get through them fairly simply. So moving on to the next question, and anyone can feel free to jump in on this one first. Tell me about the notable projects that you've been involved in, where the success of the project really hinged on the lens that was applied on that decision.
I'll let one of these guys go. I've done too much talking already. I'll let somebody.
No, it's. I also have a question from one of the listeners. So I'm going to try to tackle both of them. So one of the main projects that we are currently doing is we have a global rollout with one of the biggest OEMs in the world. And again, one of the major selling points and one of the major design positive points were basically all the simulations and the insurance that we gave to the customer, that when we installed the system and we did all the FATs, the acceptance tests with the customer about all the cameras and all the lenses and all the positions and all the output that we were getting from the cameras, they were very impressed that we were able to prove it theoretically at the beginning and prove what the performance would be without even installing the system. And to touch one of the questions that we had from James, they say that I mentioned about needing to do lots of simulations before trying the design in real life, and how often do we find that the manufacturer of these designs have introduced like unforeseen effects in the real world? That is an excellent question, and the honest answer is that in each and every system that we build, we find a problem that we never accounted for. And we have to improve the simulation, and we have to keep adding things. So every single time we get things and we see things that we never seen before. Like, for example, in a specific situation, we had the light from the factory shining inside the system from a weird angle for that specific vehicle type that we never accounted for. And it was, creating a glare on the sensor, and it was creating, problems to the AI and to the machine learning. So yeah, every time we learn something, or there was some new vibrations that we never accounted for. We installed a new system in the body shop area, which is on a mezzanine. Hanging from the ceiling. So again, the vibrations there are totally different to what we used before. So yeah, having to do lots of simulation and proper design to account in multiple different scenarios, basically.
Okay, thanks, Spiros. And Tom, are there any from your point of view, but not going over any NDA clauses, are there any details that you can share with us of past projects where the decision on the lens application has really made the success?
Yep. So there's one application that we had fairly recently, which was electronic component inspection. But there I'm going to go back to what I said in the previous for the previous question about space constraints. This was exactly this problem here, where we were given a very, very, very small amount of space to design a telecentric lens. So just to give some context, the lens had to be basically half the size of my pinky finger. So really, really, really small. Typically, telecentric lenses, as mentioned before, they have to be given space in order to achieve that telecentricity effect. So here we were working with the very, very constrained requirements. What was helpful in this case was that the customer was able to relax the telecentricity spec a little bit. So that's basically, if you think about the telecentricity spec, is how parallel are my chief rays going to be, the rays that determine the magnification. And so they allowed for a little bit of divergence in their telecentricity spec. So this helped us really make our design much smaller than first anticipated. Another aspect, one that Spiros mentioned as well, is we need to do a lot of simulation for this. It's very much so a case of doing as many simulations as possible. And then when it comes to the testing, having the testing to confirm those simulations, if necessary. Often we try and avoid unnecessary testing, because that involves creating new test beds, extra length on in the design procedure, in the manufacturing procedure. So if we can get away with doing simulations and without having to do additional testing afterwards, then that would save a lot of time and a lot of money for the customer. So these were some of the requirements for this particular application. Maybe something else to measure is also the type of material being used. Because we're dealing with such crazy space restrictions, we had to consider as well the type of housing we're using, and we had paper thin housing basically. So it was really important in determining what material would be acceptable. Also, what type of coating are we putting on this metal material? Because we don't want anything like stray light going into the optical design, where then you would end up having artifacts going onto your sensor, random bright spots or random dark spots. So this is really something that we want to try and avoid. So there's a whole range of different issues that come into play here.
Right, yeah, so testing and more testing, but simulated testing is the answer there. And Simon, was there any kind of projects that you could share with us?
Well, yeah, a lot. I'll kind of change the discussion point, rather than thinking about how you work things out on paper particularly, or simulating things. more to do with a little bit of out of the box thinking is sometimes required. I can think of a couple of applications where, for example, we had an application where space constraints, very similar to what Tom said, became an issue because a customer was using a line scan camera, which typically has quite a long sensor inside, and therefore you need to have an optic that has a large format. We haven't covered format of lensing yet, but basically a lens has what's called an image circle behind it, and you can accommodate a sensor up to the diameter of that image circle. So as you get a bigger sensor, you need a bigger image circle. Typically, the bigger the image circle, the bigger physically the lens is. And rather than, most people, when they think about camera lenses for the type of camera we use, a C-mount lens is the first thing that comes to mind, which is, it screws into a thread that's approximately 1 inch diameter, and therefore you've got a 25 millimeter hole in the front of your camera. If your sensor is any bigger than that, it's not appropriate to use a C-mount. So you end up having to go to the next thing up, and typically that becomes something like a Nikon mount, which is sometimes called F-mount in our world, which is a bayonet fit, much bigger diameter, has a much bigger what's called flange focal distance, 46.5 millimeters versus 17.5. So, all of a sudden then the camera is much bigger, let alone the lens you're going to put on, which is also much bigger. So this particular application I'm talking about, what it turned out, although the sensor in the camera was over the length that pretty much any C-mount lens could do, it turned out that the customer could live with not using the whole sensor and do what's called partial scanning of the sensor. We managed to get the largest possible format of C-mount lens, which is a 4/3 inch, so-called, which can accommodate anything up to 23 millimeters long. Well, actually, their sensor was 28 mil long. But what we did is we came up with a scenario where we did some testing with these 4/3 inch format lenses, which are infinitely smaller and screw into this C-mount configuration, which again is much more compact. And they actually got away with it. And it was really quite something you wouldn't have immediately thought of. If your sensor's a certain length, everybody just thinks, okay, well, you've got to screw a lens on there that accommodates the whole sensor. Sometimes you don't. Sometimes just think out of the box a little bit there. Another one that comes to mind is we already mentioned about the ruggedization of lenses. Well, sometimes it's not just about ruggedization. When you think about a customer that wants to put a lens onto a camera and they want the same result, exactly the same depth of focus and same performance every time, then when you have an adjustable iris, it's never very precise. I think everybody will agree. You sometimes you get little clicks as you click down the F number on a lens, and if you compare one to another, there's always very slight variation, which means there's always very slight variation in results also. So that kind of orifice plate that I mentioned earlier for ruggedization could also be used to give you a much more accurate F number. Now, F number, we haven't explained what F number means. F number is a ratio of the focal length over the area of the hole in the iris, effectively. So when we talk about F numbers being, there's set F numbers, F1.4, for example, then it goes to F2, then F2.8, and you think, well, why is it F1.4 to F2 to F2.8? Those numbers aren't sort of whole numbers. You'd expect them to be 1, 2, 3, 4, 5, whatever. It's just because that area is got pi in it. And therefore, the difference between F1.4 and F2 means you've got a hole that is exactly twice the area of the next f-stop down. So people talk about f-stops. One f-stop gives you twice as much light, or half as much, depending which way you go. And therefore, sometimes that F number is quite important to be accurate. So again, the idea about using a plate with a fixed, machined hole in it is actually quite a nice solution to that. Other things like, traffic applications. I know everybody's going to look at the sky at this, but, traffic applications use not just the visible spectrum that we're all thinking about right here. They use a lot in the near infrared, which of course your eyes can't see, or can't see much of, let's say. And you need to be thinking about whether the lens can actually resolve or what the MTF of the lens is and its focal plane in the visible versus the near infrared. Because it's not just about color correction, which is the first thing everybody thinks about. It means you don't have to refocus between in the visible and the near infrared. It's also about what's the performance of the lens, because that MTF can a lot of the time can drop away in the near infrared. And also even the transmission of the lens can really drop away in the near infrared. So choosing that right lens and thinking about what you're going to do with it is massively important in an application like that. The only other way is to separate it with two cameras, one looking at the near infrared, nicely focused with a lens that's got very good performance in the near infrared, maybe 850 nanometers, something like that, and a separate one that does the visible, that tells you what the color of the car is and the model and all the rest of it, in the case of traffic applications. But there's loads of applications like that. Again, I think I've overstepped my talking. So yeah, hand back. Just a few ideas.
Just something to add to that as well, if you don't mind. It's also sometimes cheaper to have two systems, one for the visible and one for the infrared, than have one that does everything. So it's always worth considering, if you have the space, sometimes it's worth going for that option instead of having a lens that can do everything.
Yeah. Sometimes a compromise isn't as good as bespoke, you know.
Yeah, and I never knew that about the origin of F numbers. That's interesting as well. So we're getting down to the real kind of meat of the sandwich now. But when we're talking about choosing different lenses for specific applications, what are the specifications that you use when making your decision? What are the different specifications of the lenses? Spiros, if you could take that one.
I think we've the main key points and the buzzwords, I think we've mentioned them already. But you know, as an engineer, I can sit here and we can talk about trade-offs between using a specific sensor or another lens, and we can sit here all day and talk about them, right? We've discussed is like, is it the depth of field that you're looking for? Is it what's your where is your focal plane? Is it do you want to have a specific camera in the lens in our application for specific vehicle types, and another camera as you know, as Thomas said, do you separate the two cameras for the infrared and for the normal spectrum? Is it do you specify different lenses for different vehicles? Do you have others that are zoomed in and others that are wide? There is like a lot of different cases, and that's the beauty of the computer vision that we're trying to and the optics. It's a trade-off game, and obviously if my upper management also was here, like the first thing they would say is like, yeah, I know you can make a perfect system, you can put as many cameras as you want in there, but I also want a perfect chip system, right? So we didn't touch in terms of cost at all here, but in my application, cost is like it's a major consideration, right? We can put as many cameras as we want, as different lenses as we can, but at the end of the day, a customer has to pay for the system, and it might not be sustainable or scalable to put 100 cameras in a single system. Obviously, my procurement team will also kill me if I do this, right? So they're going to hate me if I have to have a stock of 300 cameras for one system. So it's always a trade-off and a discussion with peers like you guys or other employees that we have, and it's a discussion all the time about what do we do, how do we solve these problems.
Thanks for
basically. Yeah, it's basically a question of what you can get away with in terms of performance for the price, and it's always a balance between performance versus price. Yeah,
price actually, I've got to say, more and more so. Price is in the mix right from the start. I've got to say, go back 10 years ago, it wouldn't have been one of the first considerations. The first consideration would be let's select the right lens and then we'll figure out how we're gonna squeeze the price in, or whether we have to cut back. But I think now, because of there's a few things that have happened. One, the way lenses are made has changed a fair bit, in the fact that, you know, the precision in polishing, final polishing, even the molding process and a lot of the elements is changed quite a lot, and therefore they can be produced much less expensively. Two, you've got, you know, Chinese products have come onto the market, which originally everybody seemed to question whether they were, the quality was up to the job, and consistency, actually, more than quality. I got to say that has changed dramatically in the last 5 years, to the point where, you know, the performance that you get versus price out of something that is alarmingly inexpensive is incredible. You know, but nevertheless, when you think about price, if you have a very demanding application, actually such as what Spiros has mentioned, where you're looking for very small defects down to perhaps 1 or 2 pixels in a scene, the optical performance of the lens is absolutely critical, and you can't substitute it. So, and again, we talked about f number, right? So the biggest problem with changing your aperture is typically as you close your aperture down. So in other words, as the f number gets bigger, so you've got f8, f11, f16, your optical performance of the lens, your MTF, will usually get better and better to its optimum. Usually around f8, f11 is usually, I mean, don't get me wrong, it's still pretty good above f4, f5.6. Loads of applications say, I can't use f4 or f5.6 because I haven't got enough light, which means I have to open the lens up to f2.8 and even beyond that. The problem when you do that is it gives you the worst performance of that particular lens, because you've got all the edge effects. Your depth of focus is then really, really narrow. So your depth of focus increases as you close down. All those things change as you change your iris size. And then, you know, you get to that point where it comes down to the raw quality of the glass and the polishing. And therefore you will find that whichever way you cut it, if you want a top quality lens, you have to pay the price to have that glass in something such as a Carl Zeiss lens, for example. And you know, when you have the iris stop down, you find when I've done side-by-side testing, there's not much difference if you've got the iris closed down a bit. But if you've got the iris wide open, which some applications you just have to do that because you haven't got enough light, that's when you see the real quality of a high-end lens. And that is the way really to think about it. Some people are absolutely forced to use a top-end lens because they have to have the iris wide open. So that kind of leads us down that path. So there's all these things we think about, and it's like, oh no, we need a lens for a couple of £100. Okay, but you have to live with the fact if the iris is wide open, you're not going to get very good results. So you either get a much more powerful light and change other things about the environment so that you can stop it down a couple of f-stops, or you pay for the top end lens. So yeah.
And I think that point about cost brings us on nicely to an audience question we've had come in, which is, why is there not a wider selection of affordable special lenses, like, for example, telecentric macro lenses with high resolution? Is there anything else that you can add there on that discussion of kind of cost versus quality with those specifics?
Anybody want to speak first?
Yeah, I'll go first then. In that case, yeah, it's absolutely possible to have a lower cost, or relatively lower cost, let's say, telecentric lens. But then we're having to, in order to lower these our own costs, basically, we would have to design them for a much slower aperture. So your f10, f20, all that range there. It's much easier for an optical designer to design for these much smaller apertures, because it just makes it much easier to correct for aberrations, or let's say the aberrations that come into play are a lot less present when you stop down your lens. So it is possible to have these affordable telecentric lenses. they're still going to be more expensive than the fixed focal length lens, just because we have to deal with the size aspect. So yeah, as Simon mentioned, if you want to image an object with a telecentric lens, then your telecentric lens has to be at least the same size, probably actually a little bit bigger than your object. So that's where it comes into play. Your front elements of your telecentric lens are going to have to be the same size or bigger than your object. And that's what basically drives costs. The other aspect is typically telecentrics are longer as well than your fixed focal length lenses. And so having to have not necessarily more elements inside, but like a bigger mount to hold the lenses is also going to drive costs up. So there's those aspects that contributes really to why a telecentric lens is typically more expensive than your standard lens. And of course, if you need to design a telecentric lens that's for a much faster aperture, so your f/2s, which is probably quite difficult with a telecentric lens, but even like a telecentric lens that's at f/4, f/6, it's going to be significantly more expensive than designing a telecentric lens that's designed for f/12 or f/16 and so on.
Yeah,
Thanks, Tom.
I mean, you're right as far as there's again, I go back to this comment that I made that there's a lot more people. We have many lines of lenses, different camera manufacturers that we deal with, and going back X number of years, there didn't used to be a huge amount of overlap. We would choose to have half a dozen lens manufacturers or more, specifically because you had one manufacturer that would make telecentric lenses and specialize in that, and then you'd have large format lenses and maybe a different manufacturer, and then you'd have C-mount lenses, and you might have 2 or 3 manufacturers of those for the high end and low end kind of scale that we just talked about. These days, everybody is manufacturing the whole lot, so it means you have lots of lens manufacturers that are manufacturing telecentric, macro, standard, and a combination of all sorts. So it means that you've got a lot more choice, and therefore I think that the question about the pricing, I think you can get very inexpensive. We have quite inexpensive telecentric lenses, but when you talk about high mag, yes, high mag, but only with a very small image circle. So you can only use them with perhaps a half-inch camera, half-inch sensor, or possibly up to a 2/3 inch. A lot of sensors these days have got bigger than that. You've got a 1-inch sensor, and in the case of Spiros, I think you guys are using cameras with much larger sensors, like what we call a full frame sensor. So a full frame sensor has a 36 millimeter diagonal. 43 mil diagonal, a 36 by 24 with a 43 diagonal. So that's a huge sensor. Hence, you need quite a large, format lens to cover that. And if you wanted it to be telecentric, well, telecentric means you've got to have something the same size as both behind and in front. If it's what's called a bi-telecentric lens, which means it's collimated behind and in front. Therefore, that's never going to come down to £100. Let's call that a cheap lens, £100. Telecentric lenses are not in that category. They're always going to be more than that, for all the reasons that Tom said as well. So
yeah, that's also one
cheap.
of our.
You can get small ones quite cheap.
That is one of our main problems, also, as you said. Like the very big sensor, for us, we have to get a very big lens, and that is going to be expensive, no matter what. And the problem is, the cameras are getting bigger and bigger. The sensors are getting bigger and bigger. We're getting more megapixels as we can imagine in the last, as we could ever imagine in the last 5
Smaller
years.
Smaller pixel sizes as well, yeah.
Exactly. And the problem now becomes the lens. And if you get a lens for that specific camera, it's going to be so expensive that it's prohibited. So then again, you start trading off and let's say, okay, let's add, 2 cameras with half of the resolution. Is that going to be enough? And so on, right? It's the same thing as you guys have been saying with the telecentric. Like it's a trade-offs that you have to find and find a solution for them.
If I can move on to another question we've had come in now, actually, which is there something like an EMVA standard for the representation of an MTF? And because there's an impression that manufacturers decide themselves how to present their lenses. trying to show the advantages mainly. But is there an official common denominator there with the representation?
I mean, I can answer that, but Tom, do you want to answer first, and I'll go at the end, or
Yeah,
do you want
sure.
me to answer first? Yeah.
No, I can go ahead. Well, for us, it's not. I would say generally, there's not really a definite standard out there. There's different ways of representing MTF data. For example, at Edmund Optics, we'll have your line pairs per millimeter, so your resolution on your x-axis, and then you'll have your contrast on your y-axis. So what's the difference between your blacks and whites when you're looking at those bars, those black and white bars? So that's the way that we would represent it. Of course, we can't represent every single potential MTF curve that exists for a single lens because it's an infinite amount of data in that case. So we have to select specific working distances or specific F numbers or specific wave bands that these MTF curves are valid for. If we typically, this will be for example, for us would be the visible spectrum, and then we'll set the optimal working distance at which the lens works best, and then maybe one that's a closer working distance and one that's a slightly further working distance. And then maybe some variations in the F number, but it's impossible to display on our data sheets every single MTF curve possible. So that's from our perspective anyway, is where that comes from.
Yeah, I'd agree with everything Tom said. I've got to say, EMV 1288, for anybody that doesn't know, is a standard for cameras. And it was really brought in to have some kind of consistency about camera to camera variation originally, and it set up almost like a calibrated light source, and therefore what its sensitivity was versus that calibrated light source and so on. So you had something as a referral. This whole thing that's been brought up here is a massive can of worms. It really is, because everybody has their own way of doing it, and it's not good because it makes it really difficult to compare lenses on the data sheets. But as a general rule of thumb, MTF is all manufacturers, most manufacturers, not all, they draw their MTF limit at 20% MTF, okay? So what does that mean? It means, when I was talking earlier about the difference between, what you see as a black line and what you see as a white line, when you have a 20% difference in grey level value between what you think is black and what you think is white, that is that 20% of true black and true white, I should say. So your scale has gone down to what you think is kind of a dark grey and a light grey. That's where they draw their limit. So when they say that a lens will resolve to 5 microns, or it will resolve to 10 microns, or whatever they've got on their data sheet, that optical limit is drawn at 20% MTF. So when they've got a 5 micron, and we've said 5 micron equals 100 line pairs, i.e. that's 50 black lines and 50 white lines in between, that's 50 line pairs. If you've got that in a millimeter, so you can imagine how many there are, if you've got 20% on that, that's where they say, well, we can resolve to that. Truthfully, it's subjective. Some people can't live with that. Some people can. Some people say, well, I need at least 50% MTF at 5 microns to live with. So when you look at data sheets, it's really difficult but at least it gives you a stab in the dark. If everybody stuck with that 20% MTF, then you'd at least have a good comparison. So this is a really good question, I would say. I think it's screaming the industry for some kind of standard where we do actually dictate that it has to be 20% MTF. You have to have it at certain F numbers, i.e. wide open and, I don't know, F4 or F8 or something standard. So everybody has to do it. And working distances, that's massively important. The infinity performance is vastly different in some cases to it is at short range. So again, it's a brilliant question. I'd love to see it, a standard.
Thanks, Simon. And that brings us on, I think, to maybe possibly the last question, if we've got time for it here, in terms of looking to the future and what we'd like to see future kind of developments progress the industry. maybe I'll start off with Spiros on this one then. How do you think the process of optimizing and implementing lenses and applications will evolve over the next 5 years, let's say?
Well, we've seen already like a huge spike in terms of the cameras that we have. Like even your smartphones now are starting to get bigger and bigger sensors on it. The main thing is the way I see it is with all the deep learning and all the machine learning stuff that are increasing in the last few years. Focusing on images is going to be far more important than what it has been in the previous years. Like you have to give all these machine learning algorithms the best possible data that you can. For us, as I mentioned earlier, we are looking at the highest end possible cameras and lenses to give the best possible chance for our customers to find their defects. And that is causing us a huge headache on the cost because every time the high-end stuff are always expensive. Like a good comparison would be like if you see all the latest news with all the GPUs, for example, that are coming out every year, every year you get a new generation of a GPU, which is far greater than what it was before. The cost has increased, but maybe slightly. So I want to see that happening for the sensors and for the lenses, right? I want to see that generational improvement year after year, but the cost not going through the sky, because that is going to be impossible for us to use them basically.
And Tom, maybe is there anything that you'd like to add about what the kind of trends you're seeing and in the technology and how that might progress?
Yeah, just to kind of piggyback off what the Spiros was saying, I think there's going to need to be some major changes in lens manufacturing techniques. I think an increasing amount of molding, especially for aspheres, let's say, because aspherical elements used in lens designs, for example, often they're still, in many cases, they're still polished or grinded and then polished, whereas to make them cheap, you have to have them molded. And the main cost from that is the cost of the mold itself, generating a mold. And then it's only really worth, at the moment, doing it in high quantities. If you start doing molding for very low volumes or for, let's say, medium to low volumes, it's the cost is still quite high. So really bringing that down, I think, would make a big difference. But also I would say the availability of glass types. I think that's something that's not really spoken about too much. There's a lot of glass types out there used in lens designs that are extremely cheap relative to others, and that's just to do with the fact that there's limited supply of specific types of glass, and they're not made in the same quantities for each different batch. So you end up having the major glass manufacturers that are just doing a batch of a specific glass that they plan on lasting 4 years, and they never touch it again. And so you end up with glass shortages for specific types of glass. And I think the more types of glass that we have available to choose from when designing a lens, the cheaper we'll be able to make that lens.
Thanks. And how about from your side, Simon? What are you seeing projecting?
Same as above. I've got to say there's always been at the low end using, rather than glass, they use polymers, and they mold them exactly the same. But of course, they're much easier to manufacture. You can imagine even when you're molding glass, it's quite an undertaking molding glass. It's not the same as most polymers that is effectively a resin based kind of setup. Now CCTV cameras have used that kind of technology for a very long time. They are getting better and better, so we are seeing some of that come through. Another thing that we've mentioned so far is things like liquid lenses. Everybody starts to rave about liquid lenses as well. Now, there's lots of compromises in liquid lenses from my view. And repeatability and everything kind of is another big question mark over it. But they are inexpensive to manufacture once you've actually set up. and you can change the focal length of them. So for focusing and that kind of stuff, by changing the shape effectively of the front element, which you can do just by, changing the amount of liquid, just moving the liquid around a little bit inside, then they've got their place, I guess. But we just don't see that. What we do see as a trend is we are selling more and more and more lenses that are coming in from China that are very, very good, honestly, and especially for the price. You just wouldn't believe, in a 10-year period, 5-year period, things have almost gone down by an order of magnitude, which is just eyebrow raising. What was well, maybe not £500 to £50, but in that ballpark where you've got something that was several £100 now down at £50-60, and when you look at the performance, there's so little in it. I think there's the answer to your question. I think it says a lot of engineers now seem to be looking for lenses that are good enough. Things don't seem to be optimized like they were. And probably a lot of that is connected to exactly what Spiros said, and that is that things are being done with so-called AI. And I hate the term AI, deep learning that we think about, neural networks that use deep learning, and, tens of thousands of examples that have gone in because computing power has gone through the roof. You can build neural networks with this kind of deep learning underneath. And therefore, do we optically need things quite as good as we used to? For lots of applications, probably the answer to that is you can live with more compromise. And so there's where I see it going. I think that unfortunately for Spiros, there's no chance, because unless you can see a scratch that is 1 pixel wide or a couple of pixels wide for him, then it doesn't matter. Everything you do after that, from a deep learning point of view, is irrelevant, because if you can't see it in the initial image, you've had it. So MTF, MTF, and MTF. It's like location, location, location on TV. Resolution is everything. So there we are. That's, from my side, I'd say a good time to for people to think about that. Right.
Those cost reductions sound like they're really opening up and kind of democratizing the sector, which is one of the good points. But that's about all we've got time for, I'm afraid. So there's just time left to thank our 3 guests again, Spiros, Tom, and Simon, for taking the time to discuss the subject with us. As I mentioned earlier, the web panel will be available on demand in the webcast section of Imaging and Machine Vision Europe for 12 months, along with previous recordings from the Visionary series, so go and check those out later. The next discussion we've got coming up in the Visionary series will be live on the 12th of April, when we'll be discussing how to overcome some of the major lighting challenges posed by imaging applications. So I look forward to that. But until then, I hope you enjoyed today's discussion and have a good rest of the day. Goodbye.
Thank you very much.
Thanks, everybody. Bye.
Thank you.